So this is ECE 4760, which is Digital Systems Design with Microcontrollers. My name is Hunter. I'm actually one of two instructors for this course this semester. The other instructor, I think a lot of you know already, is Bruce. Bruce, you want to just say hi to everyone?
Morning. So happy to see everybody virtually here.
So Bruce and I are going to co-instruct this course in much the same way that we co-instructed the 5760 course last semester, which is to say, generally speaking, I'll do the lectures with Bruce being welcome to jump in at any time. And then Bruce and I will do the lab sections together. So you'll get to know both of us really well. What I want to do today is, to the best of my ability, attempt to answer the following three questions, which is, what's the structure of this course? What are you going to build this semester, and how are you going to build those things? And the reason I want to dedicate an entire lecture to trying to really thoroughly answer this question is simply because this is kind of a weird semester. This is the first time that this course has ever been taught remotely. So it seems to me that a lot of you may be wondering precisely what you signed up for. So I want to try to make it clear exactly what you've signed up for. And then I want to talk about what you're going to build and how you're going to build those things by doing some demonstrations of the labs. So lab demos are always a little scary, but we'll try to show you what you're going to be building. With regard to structure of the course, despite the fact that this course is remote this semester, the structure is the same as it has always been. This is a hardcore laboratory and design class. So as usual, this course is going to have a series of laboratory assignments, each of which lasting a few weeks. In this particular semester, we're going to have 4 laboratory assignments, each lasting 2 weeks, and each of which will culminate in a demonstration of some sort. So you'll demonstrate the thing that you've built in that particular lab assignment. And the idea is that each of these lab assignments is putting some additional tools in your tool belt. And after the last one, you'll have the opportunity to deploy those tools in a 4-week, totally open-ended design project to build anything that you would want. Anything that you would want within the limitations of the infrastructure for the remote learning course this semester, and anything that is legal and within reason and these sorts of things. But generally speaking, anything that you find cool, you can build. And if you go through the course website and look at some of the stuff that folks have built in previous semesters, it's wildly diverse, right? So generally speaking, we encourage folks to think about something that you're interested in. Could be something totally unrelated to engineering, and come up with some sort of a project that explores that interest. And those sorts of projects tend to work the best. Each of these lab assignments is going to have an associated lab report. So after your demonstration, a week after that demonstration, you'll be asked to turn in a lab report. And the specifications for those lab reports are laid out in a fair amount of detail on the course website. So I won't go over them too much, but it's all the typical sort of lab report stuff in there. Those lab reports are the only sort of homework that you turn in for this course. So there are no tests in this course. There's no homework in this course other than the lab reports. The idea is that all of your learning for this class is going to take place in the laboratory in the process of building things. Which is not to say that these labs, for that reason, because there's no tests and because there's no homework, these labs are long and they require quite a bit of time. So you should expect in this course to be required to put in lab hours outside of lab sections. So each of you will come to lab once a week, and those lab meeting times are 3 hours each. So in those 3 hours, both Bruce and myself and a couple of your TAs will be there to help you debug and come up with design ideas and that sort of thing. So in some regard, those lab hours also double as sort of office hours to help you work on these projects. But you should expect to put in hours on these projects outside of the lab sections as well. And I should mention too, your TAs. Your TAs for this course are going to be Megan, Priya, Sujith, and Andrew. And we're very lucky to have these folks as TAs for a lot of reasons, but one of the reasons that we're very lucky to have these folks as TAs is they were all students in the 5760 course last semester, which used a lot of similar remote learning infrastructure that we're going to be using this semester. So they'll be very helpful in getting comfortable with how all of this is going to work. Anything else with regard to infrastructure? I'll say this is sort of implied by what I've already said, but this class is perhaps a little different than other courses that you've taken in that it's very much an objectives-based class. So for each of these lab assignments, we specify a thing to build and the specifications for that thing to build. And the purpose of these lectures is entirely to help you build those things. So it's not like some other classes where there's sort of a laundry list of items that we have to get through this topic and then this topic and et cetera. It's a lot more flexible than that. I have a bunch of lectures prepared to go over the topics that I think will be most helpful for you in the lab sections that week. And I have them prepared to go over them in the order that I think will be most helpful. That being said, it's very flexible. So if we get into lab section and we discover that there's a particular topic that's causing people trouble, then we'll do a lecture about that topic. Or alternatively, if I have a lecture planned for some topic and it becomes clear in lab section that people are very comfortable with this already, then we won't spend lecture time talking about that, and we'll talk about something else. So stay very, communicate with me a lot about this stuff, because I am very happy to make these lectures whatever they need to be in order to be most helpful to you. But in order to do that, it helps to have some feedback from you folks. Any questions about course structure before I move on? Okay. If anyone has any questions, you can either just interrupt me or put something in the chat and it'll pop up on my screen. Before I get into the lab demos themselves, I thought I would just briefly answer this question because I've gotten it from a couple of different students and some folks that aren't students. So I want to just try to answer it. And the question is, why are we doing this class like this? This is a hardcore laboratory and design class that in a typical semester involves a lot of prototyping with your fingers and hands and stuff. So why have we set up the course so that you're doing remote access to in-lab infrastructure? And it was a decision that was made thoughtfully. And I just want to briefly go over the thought process in making this decision. The fact of the matter is that the social distancing constraints here at Cornell for this particular semester are such that in-person labs for this class were not really a practical option. Cornell is allowing for students to come to labs, and you may be going to labs for some of your other classes, but in order to be in compliance with the social distancing guidelines, every student in that lab needs to be 6 feet from every other student in that lab, and the instructors also need to be 6 feet from the students, which makes hardware debugging really hard and makes working on hardware as a group basically impossible, right? You'd have to be 6 feet from all of your group mates. So we're sort of in a remote learning world for this reason by default. Now, if you're going to teach a course like this remotely, there are at least 2 strategies. There might be more strategies, but there are 2 that occur to me. One is to put together kits and to mail those kits to students, and so that students can work on these labs in their own homes and apartments. And the other one is to do what we're doing this semester, which is have all of the hardware maintained in the laboratory and then have students remotely access that hardware via remote desktop in our case, program it and debug it, and do all that stuff from elsewhere. We're going with the second option for a few reasons. And I'll mention too that we're going for this second option this semester, and this is a learning thing. So if we do this for a few more semesters, things may change. I don't know, but we're going with this semester for a few reasons. The first is informed by friends and colleagues that I have at a lot of the companies where many of you will go work in the coming months or years. And what I've learned from these folks is that at a lot of these companies in the time of COVID, they've taken the approach of setting up their hardware labs for remote access. So the strategy at many of these companies has been to put a skeleton crew of technicians in a hardware lab to do things like move scope probes and that sort of stuff, and then have many of the engineers remotely access that hardware, program and debug it from elsewhere. And we did this for 5760 last semester. And the reason that I'm inclined to do it again this semester is one of the things that we learned in doing that course that way is that remote access and debugging of hardware is a skill. It's something that is, it's different than working with working with hardware that's directly in front of you. And at least for the time being, it's a field relevant skill. It's something that's actually marketable. And I view one of my responsibilities as an instructor here, and particularly as an instructor of this course, to be to help students learn skills that are immediately applicable in industry. And for the time being, this is one of them. For the time being, remote access of hardware is one of these skills that if you go get a job in the next year or so, you may be doing this. And in fact, it's quite likely that you'll be doing this. So I feel a certain obligation to get people comfortable with it. I don't know how long that's going to be the case. It may be the case that by this time next year, this is no longer a relevant skill. However, I'm not so sure about that, because one of the other things that we learned from 5760 last semester is it's pretty nice to be able to access hardware remotely. Obviously, there's some stuff that it's way better to be there in person to do prototyping, but there's a whole category of other tasks that, boy, is it nice to access this stuff from elsewhere. So I'm not so sure that this is a skill that's going to leave the industry tremendously quickly. I think in some regards it'll stick around for a while. The other reason that we're doing this course this semester is that I tend to be pretty risk averse as a person, and it seems to me that the likelihood of some disruptive event happening this semester is too high for me to ignore in putting together a class. By some disruptive event, I mean something like the university saying, okay, nobody's allowed on campus anymore. Or the university saying everybody has to go home and people have to change their location very quickly. In setting up the course like this, where you guys are going to be remotely accessing hardware that's maintained here in the lab, as long as folks can maintain an internet connection, then this course can continue pretty much unperturbed. So we're pretty robust to chaos by setting up the course this way. Not entirely robust to chaos. And if something chaotic happens in your life that's preventing you from being productive, just communicate with me and I'm going to be very patient with you about that. All that I ask is that you do the same for me in return. We're using a lot of new infrastructure this semester. Bruce and I have tested it really thoroughly as we can manage. But that being said, as soon as you put stuff into deployment, some unforeseen error pops up. So I have no doubt that there are going to be small technical hiccups here and there. When you encounter one, all that I ask is that you communicate it with me quickly. I'll solve it as quickly as I can, and that you be a little patient with me as we work out any little kinks that we might encounter in the first week or two. And then I'll just mention that the third and final reason that I'm inclined to teach this class like this semester is this is a university. And in my view, one of the things that a good university should be constantly researching is how best to teach. And we're in entirely new circumstances right now. And it is not known really how best to teach content like this in these circumstances. And in order to figure that out, you have to conduct experiments. You have to do research. And in my view, the experiment of packing up kits and sending it to students is being conducted. That experiment's being conducted by a lot of other courses here at Cornell, being conducted by a lot of other universities elsewhere. This experiment kind of isn't being conducted, as far as I can tell. And I think that there's interesting things to learn in doing this experiment and seeing how a course like this, taught like this, goes, what we can learn from it. So for that reason too, we're doing the course like this semester. Are there any questions about this? I'm going to next go through some of the infrastructure that's in place and then demo some labs. But if anybody has any questions, I'm happy to answer them. Okay. So let me start by showing you what is set up in the lab. So in the Philips 238 lab, I'm pointing this way because I'm talking to you from Philips 208, which is the office that I'm sitting in. So Philips 238 is that way. In the Philips 238 lab, there are 19 independent lab stations set up, each of which has the infrastructure that's pictured on the screen now. So you'll work on all of your lab assignments in groups. I strongly recommend groups of 3. Some groups of 2 are okay, but I strongly recommend groups of 3 just because of the amount of work associated with each of these labs. But because we're going to be working in groups, that means each of your groups will have your own dedicated lab station, and you will not have to share this infrastructure with anyone else. You'll have your own lab PC, your own PIC32 microcontroller, all of your own equipment. So I want to talk through exactly what equipment you'll have at your disposal for this class this semester. The sort of central target board here is pictured in the middle. This is, on the course website, this is the big board, right? So this is the board that has the PIC32 target microcontroller on it. And it has a couple of other pieces of hardware that we'll use extensively throughout each lab. It has a 240 by 320 TFT display screen. So from the PIC32, you can display content on that screen, and there's a camera pointed at the screen so you can see what's there. Really useful for debugging, and we'll use it in a number of labs as sort of the object of interest that we're manipulating. The other piece of hardware of interest on this board is the DAC, the digital to analog converter. The first lab, as I'll show you in a moment, is a sound synthesis lab. So you'll be communicating with the DAC over an SPI channel, and then that DAC will send voltage waveforms out through, in a typical semester, we would send that to a speaker and you would hear sounds being generated by the speaker. This semester, we're sending those sounds into the microphone input of the lab PC so that you can open up a Zoom call and hear the sounds that you generate through your headphones. We did this in 5760 last semester. It works remarkably well. You might have to play with the sound settings in Zoom a little bit just to get it to reduce the filtering and such so that it sounds okay. But you'll be able to hear the sounds that you generate quite nicely through Zoom. So this is the target board, PIC32, a TFT display screen and a DAC. And then if we just sort of go clockwise around here, on each of your lab stations, you'll also have a software controlled oscilloscope. So this is an oscilloscope that you manipulate in exactly the same way that you are used to manipulating oscilloscopes. It does all the normal oscilloscope stuff. It's just all controlled via software. So it's a 2-channel scope. At the start of each lab, I'm going to place those 2 probes at the 2 locations in the circuit where I think they'll be the most helpful for debugging. And that's where they will start. If you want these probes moved, just ask me. So for each of these labs, you'll have access to the full schematic for that lab, exactly all the hardware connections, and you'll be told where the probes are starting. If in your debugging process, it would be helpful to see some other part of the circuit on the scope, just to ask, and myself or one of your TAs will move that scope to a different location. But these are really cool. I've been playing with these quite a lot, and they do a lot of interesting stuff. Do FFTs and stuff on them too, which is kind of nice. There's attached to each of your boards, there's a pan tilt servo assembly. So this is a couple of motors that allow you to turn like this and then to tilt up and down. This is really, we're going to use this in lab 4 where we're going to create a little robot with which you interact via Zoom. I'll demo this in a moment, but it's a pretty endearing little robot that kind of looks around board, and then when you yell at it in Zoom, it looks at you. So that's going to be the subject of lab 4. This other printed circuit board here is one that we put together specifically for remote teaching this course. So this contains a lot of the hardware that would typically be on the whiteboard if we were doing this in lab. So a lot of the stuff that you would prototype yourself, we have on this external printed circuit board just to make things a little more stable. And then it's connected to the PIC32 target board via a bunch of jumper cables. But this is, we talk to the pan tilt servo assembly through this board, and then 2 aux jacks come out of this board also. One of these auxiliary cables goes into the microphone input of the lab PC. So this goes, you can generate sounds with the DAC, goes into this auxiliary cable and into the lab PC so that you can hear the sounds you generate in Zoom. And then the other one comes from the microphone or the headphone output of the lab PC into one of the analog to digital converters on the PIC so that you can talk to your microcontroller and it will hear you. You can talk to it and you can sample that sound and do digital signal processing on the sound. Or you can open up YouTube and play songs into it And in lab 3, we're going to be playing with that capability. We're going to be doing real-time spectrograms where you'll play music and songs into this thing and create spectrograms. There are a couple of cameras at each lab bench for looking at all this equipment. One of the cameras is sort of leaned back to give you a view of the whole bench. This is particularly useful for lab 4, where you're going to be watching this robot move around. The other camera is leaning directly over the TFT display so that you can see what you're putting onto that TFT display. There's a little debugger that we use for actually programming the PIC32 microcontroller. And then each station also has an external hard drive plugged into the lab PC. This is a lesson learned from 5760. Only one person can remote desktop into these PCs at a time. So what that means is when you're working as a group, one member of the group will remote desktop into the PC and share screen. And then the other members of the group can help write the software, either but just by communicating through words or by allowing group members to control screen. But in any case, because this external hard drive is here so that you can have permanent file storage between users of a lab PC. So instead of having to button up all of your work and email it to one another or put it on Dropbox or something like that, each of you will be able to store all your work locally on an external drive, and then separate users can access that work. So that's everything that you'll have access to. This is a slightly different view of all that stuff. So this is the little debugger, the target board, the oscilloscope, a couple of cameras, and the external PCB here. Any infrastructure questions? There's a lot of infrastructure here. We're not going to use all of it every lab, and you'll get comfortable with it as you use it more. The first lab, so our first lab for the Monday people is today. In the first lab section, all that we're going to be doing is basically going through and getting comfortable with the workflow and using this infrastructure. And then the first lab proper starts immediately after that. So for the Monday people, the first lab 1 checkout will be a week from today. So I want to show you those labs now. As I do, I want to talk about what goes, all of the labs this semester are new, which is pretty exciting. And they were all designed specifically for remote teaching, and they were designed to meet a few different criteria. So I want to talk through what those criteria were so that as I go through these labs, you can keep an eye out for these things. They were all designed aiming to achieve the following goals. The first aim for each of these labs is they're supposed to be self-motivating, which is to say, we're never going to ask you to build something that seems arbitrary or contrived. Something like generate a 50 kilohertz square wave with plus or minus, this tolerance. Yeah, that's useful for a lot of applications, but it's not exactly exciting in its own right. So for each of these labs, the idea is that by the end of that lab, you will have built something that you can interact with and you can play with, or you can learn something from. And in addition to building sort of the central intelligence of that lab, you're also going to be building a user interface that is simple enough that any non-technical person could also play with it. So if you're taking this class remotely from your home someplace, the idea is that everything you build, you will build it with an interface that's simple enough that a non-technical member of your family or a non-technical friend could play with what you've built and enjoy it and understand it. All of these labs are also designed to be extensible. So if we're doing a particular lab and you find it really interesting, and I hope that you will, the hope is that they're all designed so that if you want to run with something, there are places to run to. So they are all extensible. There's a certain amount of goals for each lab. And then if you want to go beyond those goals, there are very interesting places to go. And some of you will do that for some of these labs. Like I said, they're all designed to add tools to your tool belt so that by the time you get to the final project, each lab will have exercised a few different skills so that you can deploy all those skills on whatever you want to build. And then very importantly, they were also chosen because I find them cool. And this is more important than you may think, but it makes my job so much easier when I find what we're doing really interesting. And one of the major reasons that all of these labs were chosen is I find them incredibly interesting, which just hopefully means that you'll have more fun doing them as well, because hopefully you'll find them interesting too. So let me show you what we're going to be doing. Anybody have any questions? Okay, so I already have a remote desktop connection open here. In this case, I have it open to the lab PC that's sitting right next to me, but it's set up identically to the ones in the lab. And I want to start by just showing you the demo code that will be provided to you. So in lab 1, we're going to go through the whole process of creating a new project, importing some demo code and loading it onto the PIC. So I'm not going to go through that in real time here. I just want to show you what the outcome is going to be. So when you run the demo code, you'll load some embedded software onto the PIC, and then you'll run this Python program that allows for you, it's your user interface to the PIC. And if we open up a camera here, we can see the TFT display screen of the PIC here. And we can see that through this user interface, we can interact with it. So there's a small line here. By moving this, we can move the line. There's a small dot here, the color of which we can change. Okay, so very simple interactions. The idea of this starter demo code is that we want to give you all of the basic tools that you can manipulate for various coming labs, right? So the idea with this user interface is just that there's a whole bunch of different user interface things here. There's buttons and there's sliders and there's toggle switches and drop-down menus. You're not going to use all of these for every lab, but the idea is that we want to show you a demo where all of this stuff is deployed so that you can strip stuff out of that demo for a particular lab, add stuff to that demo for a particular lab, etc. The other thing that this demo is doing is direct digital synthesis of a sine wave. That sine wave is being sent through the auxiliary cable into the microphone input of the PC. And if I've joined this Zoom call from this PC. So if I unmute this, we should be able to hear the sound that it's generating. And then we can change the frequency of that sound. So like I said, the quality is, you can play with the audio settings and you can get it to sound nicer than that. But that's essentially what we're going to be doing. So let me show you the labs proper. In order to do that, I'll exit this and I'll start first with the birdsong lab. So I'm programming the PIC. In the first lab, what we're going to be doing, there's sort of a theme to these labs this semester because lately I've kind of been interested in ornithology and stuff. So it's kind of bird themed labs for the first few labs. In the first one, we're going to be synthesizing the song of a northern cardinal. I imagine many of you know what a northern cardinal looks like, but let me just pull it up. You've all seen these. One of these guys, right? So really pretty bird, very striking red, not uncommon here in Ithaca. So as you're walking around campus, keep an eye out for these things. But what we're going to be doing is looking at the spectrogram for the song of one of these birds, matching the curves in that spectrogram to mathematical functions, and then synthesizing those frequency sweeps with the microcontroller to generate that song. And I'll show you what I mean by this. So this program is complete, and then I can run the Python program associated with this and unmute. So there are two sound primitives that make up this particular song. There's a swoop and a chirp, and we can synthesize each of them separately, or we can put this into record mode and compose the song, which is swoop, chirp, pause, swoop, chirp, pause, swoop, chirp, pause, swoop, chirp, pause, a few more times. And if we uncheck this, it'll play the song. Sounds shockingly organic, right? And if you play with the zoom settings a little more, like I said, you can get it to sound even nicer. But it produces a song that really sounds like a bird. And part of the reason for that is that this is a songbird. Turns out that songbirds produce almost pure tones. So if you match the frequency sweeps, because they're almost pure tones, all you need to do is match that frequency sweep and it sounds just right. Like I said, the extensibility of this is if you find this cool, there's a whole lot of birds out there. And the Cornell Lab of Ornithology maintains a library of all sorts of different bird songs. So if you finish the cardinal and you want to try something more challenging, you might try like a Baltimore Oriole, which has a lot more sort of jumps and different sweeps of different kinds. And then if you really want to challenge yourself, you could try something that's not a songbird, something like a loon, which has harmonics in its call. So it's not synthesizing one frequency, but a few frequencies stacked on top of one another. And that's a little bit more challenging to get right. But if you were interested in this, you could try that. Questions about this? So this is lab 1. Okay, let me show you what lab 2 looks like. In lab 2, we are going to be implementing an algorithm called Boids. Boids is a cool algorithm. It's an artificial life program. And it creates shockingly realistic simulations of bird flocking. And if you change the parameters a little bit, it starts to look not like bird flocking, but like fish schooling. So it's a fun thing to play with because as you move, we're going to create an interface that allows for you to move the parameters in real time and see how your flock responds. I'll show you this in a moment. But what's interesting is you'll start with a set of default parameters that makes it look like birds. And then as you change things, you can make it into fish, and then you can change it into something totally inorganic looking. And if you change the parameters quickly, you can simulate different behaviors, like a spooked school of fish or something like this. So let me show you what this looks like. I've programmed this. You can see here on the TFT display a bunch of what look like flocking birds. And if I run the Python associated with this, then we get a set of controls for playing with this flock. So these are all the parameters that control this flock. Right now, they're all set to, I played with this a bit and figured out parameters that gave behavior that looked nice and organic. So they by default are set to those parameters, but we can change this. So if we change things like the protected range, I should say, the way this algorithm works is each bird is basically following 3 rules. And when all of those birds follow those same rules, you get emergent behavior that looks like this, that looks like flocking birds. So the 3 rules that each are following is separation, which is to say each bird looks in its immediate vicinity, and if there's any other bird that's too close to it, it moves away from it. And this is to simulate in nature, birds don't want to fly into each other, right? So any bird that gets too close to it, it'll move directly away from that bird. So it protects its personal space. It then looks a little bit farther, at a radius a little bit farther from it, and it looks at the direction that all of those birds are flying, and it attempts to match the average direction of all of those birds. They want to stay together, right? So it attempts to fly with its neighbors. And then the final rule that they're all following is a gentle tendency towards the center of mass of their local neighbors. They want to stay together as an aggregate. So those are the 3 main rules. And then I've added a couple of other ones that just sort of make things look nicer. One is speed limits. So a bird is prohibited from flying faster than a certain speed. It's also prohibited from flying slower than a certain speed because they can't hover unless you're a hummingbird. And then the other one is just they turn around at the edges of the screen so that they stay sort of contained. But if we play with these parameters, we can get different sort of behaviors. So this slider changes the protected range that each bird is protecting. If I slam this to the side, you'll see that they all sort of spook. And it's because they're suddenly protecting a range that's bigger than it was before. And it looks kind of like it looks like something spooked them. So here, I'm going to slide this. Oh, that was kind of anticlimactic. Well, anyway, they spread out a little bit. Sometimes they pop apart a little more violently than that. And you can change all these other parameters as well. If, for example, we change the matching factor, this is the strength with which each tries to match the local direction of travel of its neighbors. If we make this really strong, you'll see that it loses all of its organic nature. they sort of just move together as a group, exactly matching one another's direction of travel. And it no longer looks like something natural. There's no longer the randomness that you associate with natural things. If we turn this completely off, then we just end up with, after this evolves for a little bit, you end up with just a mess because nobody's trying to match one another's velocity. So the whole flocking thing stops working. But in any case, it's fun to play with these things. You can get all sorts of different behaviors, and it's by creating sliders for all of these different flock controls, you get a little sandbox for trying to create different behaviors. This algorithm, if you're a fan of like animated movies, even non-animated movies that use CGI, Boids is a relatively common algorithm deployed in filmmaking. So this was used in a lot of the original Batman movies for the flocking of bats. That was the Boids algorithm in action. It's been used in a bunch of video games. So if you keep an eye out for it, you can see it in a lot of media. And the other fun thing about this is it gives you a little bit of a different appreciation for birds that you see in nature. If you go to the slope in the early evening, I've noticed almost every night on my drive home from campus, there's a big collection of starlings that flies around above Ithaca every single night. So if you keep an eye out for them and watch them, you'll see that they look almost exactly like this. It's shocking how much this replicates their behavior. Questions about this? Okay, so that's lab 2. Let's look at lab 3. Let's see, I'm going to exit this. Lab 3 is a spectrogram. Folks know what a spectrogram is? So you all know what you all likely know what an FFT is, right? So an FFT, fast Fourier transform, is an algorithm that allows for you to look at the frequency content of some time varying signal. So if you play a bunch of, we'll use sound as an example because that's what we're going to be working with. Sound is composed of a whole bunch of different frequencies. If you do an FFT of a sound signal, that FFT will break that sound into a bunch of, it'll show you the amount of power at each frequency. So if you were playing a pure tone at 400 hertz, then your FFT would be a big spike at 400 hertz. If it's composed of a whole bunch of different frequencies, then you would see a whole bunch of different frequencies in your FFT. The spectrogram is a way of looking at the time history of the frequency content of sound. So you take that FFT and you make the FFT of a sound signal at a moment in time becomes one row of pixels that is colorized according to the amount of power at each frequency. And then you move along, and as you move, you can see the frequency content history of some sound that you've generated. This becomes more obvious when we see it in real time. But let's see, this is now producing an FFT. In this case, this is on our Zoom call, so it's actually listening to my voice and creating an FFT of my voice. And can anyone whistle? I can't whistle. Okay, that's okay. If you were to whistle into this, you could create a bunch of pure tones, but we can put, yeah, see, whoever whistled, that was at about 1,000 hertz or so. So it's fun to play with because you can talk into it, you can sing into it, and you can look at the frequency content of your song, or you can open up YouTube and play music into it. I suppose I could do that here. Let's see. I'll also open up the user interface that we create for the spectrogram. This is a relatively simple user interface, but what it allows for you to do, as I slide this, if you keep an eye on the Y axis here, it allows for you to change the scale of your spectrogram. So if you want to look at the spectrogram, for example, of birdsong, which tends to be higher frequencies, you may want to change the range so that you can see those frequencies. Or if you're looking at whale calls, which tend to be lower frequencies, you may want to change the range of your spectrogram so that you can see more details. Stuff that I found is very fun to play into this. Stringed instruments, like violins, cellos, that sort of stuff, they have stacked harmonics. So if you play music from a violin into this, you can see the stacks of harmonics moving up the spectrogram. It's kind of interesting to look at. So if you open up YouTube and play like a Bach cello suite into this, it looks really cool. I find animal calls also really cool. If you look at the lab write-up for this particular lab, I have, I think, like 10 different demonstrations just because I got really interested in this. But whale calls are particularly interesting to play in this because they're an odd combination of pure tones, like a bird. So you'll see pure frequency sweeps interspersed with harmonic stacks. So they're sort of whistling, and then they generate sound in some way that's resonating and creates these harmonic stacks, and they flip back and forth between them. And in the spectrogram, you can see all of that. So it's really interesting to look at. Hip hop, like beats, are also really interesting to play into this because they tend to be composed of a bunch of different primitives, and you can see all of those primitives on display in the spectrogram. So it's really fun to play with. What else was fun to play with? Opera was kind of cool to play into this. In any case, let me show you the final lab then, which is the little robot. So program this. So if we open up, I'm going to switch camera views here. So we've been looking down at the TFT display screen. I'm going to switch to the bench view. You can see there's a little robot sitting here. And through this interface, we can change the way that it's looking. There's a, the sensor that's sitting on top of here is non-functional. This is just because it looks like eyeballs. On your actual robots, I haven't done it yet, but I'm just going to put a bunch of googly eyes on all of them, just so it has a little bit of personality. But this is not actually, this is a rangefinder. This is not actually calculating range. It's just to make it look like it's looking at you. But the idea here is you put this in one mode that allows for you to point it in a particular direction. So in this case, we're going to make it point directly at the camera. And then when we uncheck this, it's going to exhibit a behavior that makes it appear bored. And when we yell at it, it hears that and it listens for a particular volume threshold. And at that volume threshold, it snaps back to the programmed position. So I'm going to uncheck this. Hey, robot. And it looks around. I have to be quiet. Robot. That's the idea. And the extensibility in this one, right? I said that all of these labs, I want for there to be places to run if you get interested. The challenge with this one is how many different behaviors can you get it to exhibit, right? This is one simple one where it snaps back and looks at you. But if it might give it a certain different personality if instead of snapping back and looking at you, it sort of slowly turned and looked at you. Right? And it might oscillate between these things. So the challenge is how much personality can you give this really simple little thing where all that you can do is pan and tilt two servos, and the only way that you can interact with it is through voice. And then if you really wanted to get exotic with this, this might be more of like a final project domain level of scope. But could you get it to do things like if you decompose the frequency content of some song, using a technique similar that we use to lab 3 where we're doing the spectrogram, could you get it to do like beat extraction and dancing, perhaps? You could, there are places that you could take this. I forgot to mention on the Boids lab, the extensibility with that one is, I mentioned that there were 3 rules that those Boids were following, which was separation, alignment, and cohesion. Protect your personal space, align with your neighbors, and tend gently towards the center of mass of your local group. the extensibility there is you can add more behaviors. So for example, you could add a predator, where the idea is that the predator flies around and all of the Boids, in addition to all of the rules that they ordinarily follow, they also have to avoid the predator. And you end up with behavior that looks a lot like a hawk flying around among starlings, or like those drone shots that you see of sharks swimming through schools of fish, where they all split around it. And there are other more exotic rules that you can try. You could draw in the background of the TFT a sort of pixelated tree, and when a Boid gets near the branch, you could have it pause and rest on the branch and then rejoin the flock. So there are lots of places that you could take this to add additional behaviors. Any questions about any of these labs? Okay. And we only have 5 minutes remaining. So in that remaining time, I want to just briefly mention these final projects. As I mentioned, these final projects, they're as open-ended as they've always been. So you're free to do anything within the infrastructure available. And you should start brainstorming early, right? Because it seems like this is a long way off, but in actuality, you know, we're going to ask for you to turn in a final project proposal in, well, let me think. It's going to be probably around the beginning of lab 4, which means that's like not that many weeks away, right? And it's going to be a big effort. So it's worth thinking about something that you'd really be interested in. And just to sort of start you thinking, within this infrastructure available, what sort of projects are possible? Well, anything audio is possible. You could synthesize instruments. You could try to auto-tone your voice to do like a Post Malone style, sing into it, and it sort of changes things around. You could do birdsong generators, whale song generators, head transfer functions. These are interesting. If someone sort of is playing an instrument in the corner of the room, even if your eyes were closed, you can tell the direction that sound is coming from. And it's because your head and shoulders and hair and the anatomy of your ears distort sound waves differentially. And you can simulate that and send slightly different sounds to each earbud so that you can make it sound like a sound is coming from some arbitrary direction. And if you get that tuned right, it's difficult to tune because everyone's anatomy is different. So you have a specific head transfer function that works for your head and shoulders and hair and ears and everything. But if you get it tuned for you, it is spooky good. It can be spooky good. So you could do that sort of project. Anything FFT based, those tend to be quite popular, where you play sounds and generate dancing lights and displays and stuff like that. Anything computer graphics is totally fair game. So you can use that TFT display screen so you could create video games, fractal landscape generation, particle system animations. You could do physics simulations, make diffusion reaction systems, cellular automata, like Conway's Game of Life. You could implement that on the TFT display screen. And kind of a new variety of project that is possible, might require CIT permission, is sort of network and internet-based projects. Because a lot of the infrastructure is in place now for communicating between the PIC, the microcontroller, and the lab PC, and because that lab PC has an internet connection, you might consider scraping the internet for some amount of data and doing processing of it on the PIC and displaying something, or vice versa. You might consider some sort of networking project among groups in the lab. Each lab PC could talk on the local network to other lab PCs. You could figure out something sort of interesting to do there. So in short, a lot of different options. It's worth starting to think about. And that's essentially all I have for today. So I'll just mention before we go some week 1 logistics. On the home page on the Canvas site, there's a Google form through which you can submit your group member preferences. Please do that soon. If there are particular people you would like to work with, please indicate that. Or if you would like to be assigned to a group, you can also indicate that, and I'd be happy to do that for you. For this week only, for the first labs, those groups are just arbitrarily assigned. But for all subsequent labs, you can work with whomever you'd like, or I'll assign you to someone. That's totally fine. Okay? Any questions from anyone? Okay, so if there aren't any questions, then I will see the Monday lab people in, I guess, a little over an hour. And I will see the Tuesday lab people tomorrow. And I'll see everyone else on Wednesday morning, because we'll have lecture again before lab. I'll go through, you're welcome to sign off. I'm going to answer some of the questions that have appeared in the chat